In this lesson, we're going to introduce the concept of the kinetic molecular theory of gases. Uh, I'm kind of lying when I say that we're introducing this idea. We've actually kind of encountered this idea a couple of times already, but we're just going to formalize it so that it makes a little bit more sense. Quick review of what law versus theory is, because we're talking about the kinetic molecular theory. The idea behind law, of course, is the observation. So why is it that Boyle's law works the way it does, where when you increase the pressure of a gas, somehow the volume will go down, or vice versa. If you decrease the volume of a gas, the volume will increase. So why is it that the law is inversely proportional? That's where the theory then comes in. So the law is just the observation, the theory is the explanation. You can see here the Boyle's law, the gas particles collide with the walls of containing fewer times because of the greater volume and so on and so forth. So you see there's a lot more of an explanation behind it, and it really goes into, again, sort of assuming that there is something under the surface that we can't necessarily see, right? Because the idea is that the Boyle's law is something you can observe with the naked eye, but we can't see the particles that are responsible for that. And that's really what the theory is getting into. And that's what this kinetic molecular theory is all about. Oftentimes you'll see us abbreviated as just the KMT. So notice that the kinetic molecular theory refers to the KMT and vice versa. But really what it's doing is that we're making a model. We're generating a model. This theory is based on this the structure that we're putting together that describes the behavior of these gas particles. First of all, it says that the volumes of the individual particles themselves are negligible compared to the bulk volume of the container. So let's say, again, we have a container of gases and we have all these particles in them and so on and so forth. What they're saying is that the overall volume of this container, right, that's the actual volume that the gas occupies. But what's not of any concern, and what we're assuming to be negligible, is the actual volume that the particles themselves occupy, right? Because, again, they're three-dimensional objects. They are matter, right? Matter is something that contains both volume and mass. And yeah, there's some volume to these gases, but it's just so small in comparison to the overall thing that it kind of is disregarded. Point 2, particles are constantly in motion. Pressure comes from the collisions with the wall. Now, this again is something we've talked about before, is that the idea that these particles here, right, they're never really still, right? They're always in motion, moving around, just like any other particles, really, but these are, again, are translating in space, but they move around and so on and so forth. And they're moving in a way that is, again, nonstop, is always in a straight line, and really don't change direction until they bump into something to cause it to change directions. And then you see right here, of course, that the pressure comes from the collisions of the wall. And we discussed this several times, that whenever you hit the wall, right, that's responsible for the force. And since the force, right, that is going to be applied to the surface area of the container, the pressure, of course, is a result of that relationship. Part 3. Particles collide elastically. Now, this is a new term to us, where it says energy is conserved with no additional repulsive or attractive forces. So the idea here is that when you have two particles collide, right, that they bump into each other, the idea is that they collide elastically, meaning the resulting bounce, right, as they go away from each other, isn't really affected by any kind of additional forces. So imagine if you have, again, like two cue balls, and these cue balls are, you know, say they're instead of on a felt pool table, they're actually like on ice. So let's say we have two pool balls on some ice, and really, if they bump into each other, right, they're just going to constantly keep moving forever and ever, and they're not really going to be held back or not going to be pushed away from each other anyway. So this contact right here is perfectly elastic. Part 4. Average kinetic energy is assumed to be directly proportional to temperature. And this is one that I think also kind of makes sense. Remember, average kinetic energy, we'll talk about the word average means in a little bit, like at least how it relates to kinetic energy. But kinetic energy, again, is that motion or energy of motion, right? So if you have a particle moving fast versus a particle moving a little bit slower, right, we expect that the kinetic energy is higher for this particle than it is for the one on the right. So the kinetic energy is actually, let's get rid of this arrow here. The kinetic energy is higher for this particle than it is for this one because it's moving a little bit slower. It's also directly proportional to temperature, meaning that when we talk about temperature, right, so we have high temperatures versus low temperatures. That means high temperatures refer to the fact that there's higher kinetic energy, which means that there's higher motion, faster motions, versus a lower temperature where the kinetic energy is lower, therefore the particle movement is also slower. Now, again, some of this is fairly intuitive, and this is why I'm saying that it's not really like this is necessarily an introduction. Maybe the only part that might be new is number 3 there. For the most part, though, again, this is fairly intuitive. Now, of course, in reality, there is some repulsion and some attractive forces on each other on all the gas particles. There's also some volume that is occupying space, and that is true. But again, for the most part, experimental data shows us that it pretty much follows the KMT, right? Because we do have these values, the numbers that we can use to look at the behavior of gases, and it basically fits the laws. It fits the formulas that we used earlier at the gas laws. Okay, now applying the kinetic molecular theory to gas laws is a little bit more involved, and this is where the intuition needs to be formalized into some language. So let's talk about the Boyle's law relationship here. So Boyle's law. This right here is going to be a visual that represents the Boyle's law. All right. Now, what happens here is that we're changing volume, and therefore the pressure will change as a result. So let's talk about this. How's this going to work? Well, again, right now you have a certain number of gas particles. Remember, the Boyle's law, N is constant. All right, so get rid of that. The mole amount is constant, as is the temperature, right? Because we're not going to change their temperatures that they're in. And so what happens is that when you take the volume, like say you have this disk and you push it in, right? You force the volume to decrease into this size right here. Is that the same number of gas particles are hitting the walls, then the actual force is the same, but the area that is contained in is lower. So that means you're not going to have as much of a denominator. The denominator value is going to be smaller. So that means it gets bigger. So let's remember, though, that the space in between these, right, there's still a lot of space. The actual volume of these particles is still considered to be negligible. And that the temperature is constant, meaning these particles aren't moving faster. They're just hitting the walls more frequently, right, because there's a lot less space for them to move around. And let's hit it with higher frequencies so that pressure increases. That's how we can explain, again, the using the kinetic molecular theory, Boyle's law. Charles' law, right? Charles' law right here. This is a relationship between volume and temperature. And then we also have Gay-Lussac's law, which is a relationship between pressure and temperature. So let's take a look at that in relation to this diagram, this middle diagram right here, or the Charles' law isn't really illustrated in here. But the idea here is that, let's say we have an increase in temperature, right? So that means our pressure is constant. No, excuse me, not pressure. That means our volume is constant, as is our mole amount. So N and volume constant. So we have a rigid container, and we're not changing the number of particles. What happens here is that, again, you have an increase in temperature. So what happens to your particles is that you kind of see the little whooshy marks, little flying marks after each of these. They get bigger over here, right? There's much bigger movements. And so what happens is that the particles will then bounce around, right, as usual. They'll hit the walls, but they'll hit the walls a little bit harder, right? So they'll hit the walls a little more pressure, a little more force. And so, again, in this relationship of force over area, this stays constant. The force increases, right, because overall the particles are hitting harder. Therefore, the pressure goes up. Right? That's kind of looking back at this, thinking about this in terms of particles and so on and so forth. So ultimately, again, how is it that you need to explain things using the kinetic molecular theory is that you really just look at how the particles move, how they change, and how the container changes and so on and so forth to be able to explain how these behaviors and these gas laws are observed. Right. Now, I didn't go over Charles' law or Avogadro's law with you, but I encourage you to go and take the time right now to go ahead and just briefly talk through it. Right? See how is it that you change temperature to be able to see the result in V, and changes in V, or how you change the mole amount and see what happens to the volume. The next idea here is called the mean free path. This is where you basically track the path of a single particle. So if I have, again, a single gas particle, let's see what happens as it moves around. So it's going to move here, then move there, then move there, then move there, then move here. And every time it moves and changes the direction, right, every time it's doing that, it basically is either colliding with the wall or another particle so that it does change direction. Otherwise, it would go straight for infinity. And of course, this path is very erratic. But what they're saying here is that the mean free path is the average distance traveled by a particle between collisions, right? So you can see that some of these are shorter than others. Some of these are a little bit longer than others. Some of these are really short like that. And you have some really long ones like that one. So the idea is that the average of their path, their average distance that they move before they bump into each other, that's the mean free path. So describe what happens to the mean free path when you do all of these changes, or at least do a change to a sample of gas. For example, if you double the volume, what happens to the mean free path? Well, again, same number of particles, but now you have a bigger container, bigger area to move around in. Well, it turns out that your mean free path will also increase, right? Because that means that there's a lot more free space to move about. It's not going to collide with the wall or another particle as frequently as it did before. So in this case, the volume is doubled, meaning the mean free path will increase, right? A second inert gas is added, right? So inert gas, of course, meaning that it is an unreactive. So basically just another set of particles in there. What happens to the mean free path? Well, that means there's more particles around. That means there's more potential for collision. So the mean free path will end up decreasing because of the addition of them. Right, the third one, the sample is cooled. I'm going to let you try and figure this one out on your own, thinking about what happens to the particles as they cool down, and then see what that does to the mean free path. Finally, here we're going to talk about the Maxwell-Boltzmann distribution. The Maxwell-Boltzmann distribution is a distribution of the speeds. Now, this is something that takes a second to sort of conceptualize. Let's go start off by talking about what the distribution means. First of all, in a sample of gas, not all particles will move at the same speed, right? Because different gases, all the different particles that are in there aren't necessarily guaranteed to move at one uniform speed. In fact, they all move at a bunch of different speeds. So each speed, right, and the number of gas particles that move at that speed is called the distribution. So the word distribution, right, that's kind of talking about how it's spread out. How is it, how many particles are moving at a certain speed? That's the distribution. So quick non-chemistry examples, right? You can look through and figure out the height distribution of your classmates, right? So you might have some that range anywhere from like, 5, that's not a 5, anywhere, let's say 4 foot, 11 inches, and some that are 5 foot exactly, 5 foot 1, 5 foot 2, and so on and so forth. So basically you just go through and count how many you have. So how many classmates do you have at this height? Maybe 1, maybe 2 of these, maybe 2 of these, maybe 3 people. And so the distribution, of course, as you go through all the heights, basically shows you how many particles there are, how many people there are of that height. Or the color distribution in a bag of M&Ms, right? You have brown, red, yellow, green, blue, orange M&Ms, and basically counting out how many there are in each one. So this is kind of a little frequency showing you that height shows you about how many particles there are, and then the colors over here are listed across the bottom. Now, when it comes to the Maxwell-Boltzmann distribution, though, this is not about gas particles, it's not about M&Ms and people's heights, but really about the number of gas particles at each possible speed. So the Maxwell-Boltzmann distribution shows all the gas particles that might be in a container at various speeds. So this is again an example of the Maxwell-Boltzmann distribution on the right side. This graph right here is really nice to use to sort of illustrate the idea. So let's kind of ignore, first of all, the red and the blue lines. Let's go and just pay attention to the blue line right here. Now your axes here, your velocity is meters per second. So we're basically saying, okay, we have all the possible speeds that your gas particles can be moving. It can be from 0, 1 meter per second, 2 meters per second, 3 meters per second, so on and so forth, up to 1,000 meters per second, all up to 2,000, 3,000 meters per second. And then on the y-axis here is the relative number of N2 molecules with given velocity. So relative number, again, that's basically saying how many molecules are there of this velocity. Now, in this case, right, you can see that there's a bit of a distribution here going on. So this peak right here, this is sort of peak kind of goes up and then it goes all the way down here. Now, if we look at this temperature, 273 K, of course, is at 0 degrees Celsius, so it's pretty cold. Its particles have velocities of anywhere from 0 to about 130 meters per second, right? So if you look at the span, it kind of goes from here to here. That's about 0 to 1,300 meters per second. Now, again, we're not saying that every particle moves at every speed. We're saying that every particle has a speed, and it's anywhere from 0 to 1,300. But most of the particles move from about 300 to 600 meters per second. So most particles are in this section here. And I'm going to use this right here. So most of the particles are in this section. I'm going to kind of just generically shade this in just to show you what I mean, right? Most of the particles are somewhere in this range, right? So if you look at these, right, these are these heights. The height of this peak of this line is basically showing you effectively where the number of particles are, how many particles there are of this speed. And most of them are going to kind of in that range, right? The higher the peak, that's where more particles are. The average velocity is about 500 or so, meaning that most of the particles are moving somewhere around that range, but not exactly at 500. So not all particles move at 500 meters per second, just the average, right? Because there's some that move close to 0, some that move that close to 1,300. And so this idea is that the distribution is just showing you effectively, again, how many particles there are at a certain speed. Now, why is that important here? Well, the idea is two things. One, we need to make sure that we know that not all particles move at the same speed. And two, is that you can observe the changes as you change temperature. So let's go and take a look at the next temperature. 1273 in terms of Kelvin, that's about 1,000 degrees Celsius. That's really, really hot. So if you increase, again, the temperature up to from 0 degrees Celsius up to 1,000 degrees Celsius, you can see that what happens to your distribution. So this is the red line right now. Again, same idea, right? So most of the particles move, or most of the particles anyway, have a speed from either 0, or all the particles in the sample have speed from 0 up to about maybe 2,500 meters per second. But then also notice what happens to your peak is that they really kind of sort of flattens out, right? So it's no longer this high. It flattens out and lowers quite a bit. And most of your particles are kind of in this area here. The large majority of your particles move anywhere from about, I don't know, 600 to about 1,500 meters per second. So all this area right here is representing the number of particles that move at that speed. And then, of course, the average speed is much, much higher. So the average speed might be somewhere around here or so. It's not exactly there, but somewhere around there. Compare that again to the average speed, which is about here, 500 for the 0 degrees Celsius or the 273K. The average speed is much higher, right? The average speed is much, much higher because more and more particles overall are moving faster. Therefore, it brings up the average. And then much fewer particles are moving slowly. So not only does the peak lower significantly by increasing the temperature, but also the spread increases too because more potential speeds are possible. And that'll do it.